Quicksilver, Vision and the Flash, they know a thing or two about acceleration. In this video, I'm going to be talking about acceleration, how it's related to force and G-forces. Hi there, I'm Dr. Fitzgerald, the superhero scientist, and on this channel you'll find videos on the science and engineering behind superpowers, superheroes, and lots more besides. If you're new here, please consider subscribing and hit the bell so you get notifications on the latest videos. Let's get into it. The Flash is a speedster, and so are Jesse Quick, XS, and Savitar. But in addition to that, Quicksilver, who's featuring in the Disney Plus series WandaVision, is also a speedster. But before any of these super powered, super speeding individuals start moving very quickly, they all start at rest. So what happens when they move from being in a stationary position to one where they're moving at a very large speed or velocity? Well, they accelerate. Let's take a look at how acceleration works. In episode 6 of WandaVision, Pietro displays his super speed powers for all to see. But Quicksilver does a lot of starting and stopping in that scene. In other words, he does a lot of accelerating and decelerating. So how does acceleration work? To answer that question, let's consider an example of Quicksilver running. Here is Quicksilver at point A, and his aim is to get to point B. Quite simple. At point A, Quicksilver is at rest. In other words, his velocity is 0 meters per second. In this case, I am referring to velocity because Quicksilver will move from point A to point B. He will move from left to right across the screen, and that means there is a direction. And in this case, I'm going to refer to a velocity change. Now, Quicksilver completes the journey from A to B, and we find that when he reaches point B, his velocity is 200 meters per second, which is quite fast. The time to reach B was 2 seconds. With all of this information, we have what we need to calculate Quicksilver's acceleration. Let's do a recap on the information that we've got. We started out with Quicksilver at point A, and in this instance, at the start, he is at rest. His initial velocity is 0 meters per second. For the initial velocity, I'm using the symbol U, which is a symbol often used in physics for the initial velocity of something. He makes his way to point B, and his final velocity is 200 meters per second. In this case, I'm using the symbol V for the final velocity. And the time to go between A and B is 2 seconds. The acceleration of anything is given by the change in the velocity of the object divided by the time taken to accelerate. In this case, we have a change in velocity. We start out at 0 meters per second, and the final velocity is 200 meters per second, and all of this is done in 2 seconds. Using all of those symbols that you see on the screen and getting rid of all the words, you can write the acceleration as v minus u over t, which is the change in velocity over time taken. Fill in the values and you get 200 minus 0 divided by 2 is equal to 100. But what 100 what? Because we need some units here. And that's where we do some unit analysis. We know that velocity is measured in meters per second and time is measured in seconds. When you combine those units together, you will find the acceleration is given in units of meter per second squared. In this instance, Quicksilver's acceleration was a mind-boggling 100 meters per second squared. But how does acceleration affect you? Well, if you've ever been in an aeroplane, you'll know that one of the coolest things, in my opinion, is takeoff. You start out on the runway at 0 meters per second. The engines then roar and you start to move forward on the runway. The plane accelerates, its velocity starts to increase, and you feel that acceleration in a push on your body. It's as if you're being pushed into the seat on the airplane. This push, this force has a very important relationship with acceleration. And it all goes back to the 17th century with Isaac Newton. Yes, the same guy who had an apple fall on his head, but it actually didn't fall on his head, because that's actually a story and it's just a myth. He did see apples fall in an orchard, but definitely didn't have an apple fall on his head. He realized that the amount of acceleration or deceleration experienced by an object is related to the forces acting on the object. And there's a great example of forces at play in WandaVision. After Quicksilver says this to Wanda Maximoff,
"Don't sweat it, sis. It's not like your dead husband can die twice."
Wanda does this to Quicksilver. Before the blast, Quicksilver was sarcastically and happily at rest. Then Wanda fires a blast at him. This exerts a very large force on Quicksilver and propels him in the opposite direction. The force of the blast changes Quicksilver's velocity. In other words, Quicksilver accelerates. Quicksilver and Tommy Maximoff experience very large accelerations when running around Westview. But how do these accelerations compare to other accelerations? Now imagine if you took a tennis ball and extended your arm and then dropped that ball. The ball will have started out with 0 velocity in your hand, and the moment that you release it, it will start to accelerate. Acceleration due to gravity is 9.8 meters per second squared. That's about 1/10 of the acceleration that Quicksilver had in the example that I mentioned earlier on. In addition, this acceleration is often referred to as 1G or 1 G-force. What about the magnificence of the Saturn V rocket, which was used to launch man to the moon in the late 1960s and early 70s? During the launch sequence, the rocket experienced accelerations of up to 40 meters per second squared. Quite impressive, roughly around 4G, but still lower than the acceleration of Quicksilver that I presented in the example. And then there's roller coasters, because on roller coasters you can also experience different G-forces. In fact, depending on the roller coaster, you can experience G-forces of 3, 4, 5, even 6G, even higher. Really depends on the design of the roller coaster. While experiencing large G-forces for some time might sound really cool, it can have some negative effects on the human body. If you experience large G-forces for an extended period of time in something like a roller coaster, or if you were in outer space flying around in a rocket, it can lead to the loss of color vision, but only temporarily. You may also experience tunnel vision, where you can only see a very small area directly in front of you and nothing else around in your peripheral sight. And you may even go unconscious if the G-forces are large enough to stop blood with valuable oxygen reaching your brain. And that brings us back to Quicksilver. In the example that I presented at the start to introduce acceleration and how you can calculate it, I estimated that Quicksilver perhaps at times experiences accelerations of 100 meters per second squared, which is roughly around the same as 10 Gs. But one thing we can say for certain about Quicksilver in all of the films that he's appeared in thus far is he never passes out. He never complains about tunnel vision, and he never has issues with the loss of color. How is his body able to resist all of these issues? Well, it's part of his mutation, no doubt, and his cells have developed a resistance to these large G-forces. Thanks for watching and learning about acceleration with Quicksilver from WandaVision. I hope that you'll tune in for more videos in relation to superhero science and lots more besides. I've been Dr. Barry Fitzgerald, the superhero scientist, and until I see you next time, always think super.